Bakmış burada. Hayır o değil. Nerede? Oh.
Ben niye olmuyor? Nasıl?
Birazcık daha yaklaştırmam gerekiyor.
Nereye gidiyor bu?
Yes. So,
Hello, can all our participants can hear me?
I hear you.
I hear you.
Great. Yani beni diyorlarmış. Bir tane daha bir çek edelim ama.
Görüntü. Biraz daha zoom yapmamız lazım buraya. Bu şu gelsin.
Hangisini?
Kullanılmıyorsun.
Hem bilgisayar. Bu kullanılıyor mu?
Şu an kullanılmıyor.
Tamam.
Şey yapmak için belki de
Sen bakın abi. Ha, silgi nerede?
Yani buradan güzel bir resim de oynaması gerekiyor.
onu şey yaptım ben. Aynen. Hatta bütün ekran yap.
Bir de recording'e basılacak ha.
Evet, recording'e baktım. Baktım.
Şimdiden bassın fark etmez ya. Editlerim var ama.
Physical cloud. Cloud. Pardon, computer. Local. Gelmedi uyarı. Yapmıyorum. Yok, hayır.
Cloud computer. Okay, maybe I should announce two things before.
Yes.
Okay, two important locations. One is bedroom. Okay, when you enter the main building, okay, you enter, turn right, to go to second floor. That's bedroom. And for coffee, enter your main building, go straight, go and left.
And coffee times. So before you come, 10:30, 11 there will be coffee, tea, maybe cookies, and also in between, like from 2:30 to 3, there will also be the same stuff. Hopefully. So.
Okay, so people hear me probably, no one's messaging there, then I can start. Okay. Okay, so I will talk about level and Weinstein manifolds and sectors and their invariance. Actually, their invariance is like there are many invariants of them, but I will mostly focus on graph square category. Okay, and so the plan is first to define and say some properties of level Weinstein manifolds and sectors.
So and then bigger.
Bigger. Okay. Is this good?
The Weinstein is good. The first Weinstein is good. Yeah.
Okay.
Second Weinstein is also good.
But you need to remind me probably periodically. So yeah, I will talk about this class of symplectic manifolds first. The second part, I will talk about graph square categories. Maybe some more things, but I don't know. It depends on time. and three tools like for this Weissman Foucault category, some tools, some theorems that helps you compute or to say something about those things. And examples. And examples will be everywhere I plan, but let's see. So let's plan. So it's okay if I do this, right? So
So I think it might be better if you don't do it, or I can. So be careful, it shouldn't hit sometimes it hits the top.
This is good, right? But, okay. So first part, I will give some definitions. So exactly like the manifold. And maybe it's known to some people, but I will be safe and give definitions. So, okay, M is smooth manifold, and necessarily even dimensional. Actually, it's not part of definition, but it will necessarily be that. And there are two forms on M, which is non-degenerate, closed, two forms on M. So this two is a symplectic manifold, gives you a symplectic manifold. And furthermore, you ask this omega to be exact, okay? So plus this is exact, which means there is a one form I call theta, and that's part of the data. So actually, the symplectic manifold like this. This is that. So some properties. I mean, this needs to be non-compact. Right? I mean, one can show all exact symplectic manifolds are non-compact. And second, you can define a vector field corresponding to this one form. So let's go, this name of this is Liouville form, okay? So Liouville one form. And there is this vector field X, this is a vector field. And which we call Liouville vector field. Okay. The Liouville vector field. And this is Liouville one form. And there's this equation, omega X is theta. So with this equation, from theta I can get X, or from X I can get theta, because this is non-degenerate. There's a unique solution. Why? Because we mostly will work with actually X instead. I mean, X is. I mean, you can just draw X, and that will give you this exact structure, assuming it satisfies the conditions. Okay. So what else? So I will go to examples, but I want to first also say what Liouville manifold is. Okay, so Liouville manifold. So maybe I should not block the real. Okay, so it's like exact symplectic manifold, and even manifold with Liouville vector field X. Okay. 1 second. Satisfying. So one, I want X to be complete vector field. And second, so there's an exhaustion of X, compact exhaustion. Of M, sorry. So M1. Such that this level vector field is outwardly transverse to the boundary of that. So assume this has smooth boundary, by the way, such that X is this vector field outwardly transverse to the boundary of each this compact space. Okay, this is the definition of Liouville manifold. And okay, what else? I want to say something about this vector field. It's symplectically expanding, okay? Which means one property of this is if you look at the flow, this is the flow of the Liouville vector field. If we apply to omega, it will give you this, okay? Similar theta. Okay, this symplectically, so the vector field is expanding, okay? Second, if it's Liouville manifold, this thing is a contact manifold. What is contact manifold? I won't define it because maybe I won't even use it. So what is one odd dimensional counterpart of symplectic manifold? Maybe I will say something about this, but it's some important thing. So it's a contact manifold. Something important is it has a Reap vector field on it. So maybe I should say this. So this is contact manifold. What is it? It has this structure. So you remember we have theta, right? 1,4. So you can restrict this theta to this boundary. It gives you contact form. That's called alpha. So think like a smooth manifold with some this kind of form. Take this definition then. Then you can define a vector field called Reap vector field with this property. So define unique R vector field such that this is 0 and this is 1. Okay. For now, maybe. So I'm just defining some structures on it. Later I will use them. Okay.
Is the inclusion of MIs proper? I mean, they are proper subsets of each other.
No, it's just compact subset. I mean, if it satisfies this condition, that's all.
And you require them to be countably many.
I require them countably many, but I mean, that's one definition. I don't know if you have an uncountable many version which is equivalent, but
What is T there then? T to the power T.
this T is a time of this flow. So I have a vector field. So this T is not that thing. Okay. So this T is I have a vector field. I have
Maybe a picture
a picture of which one?
of a Liouville manifold.
Oh yeah. So maybe exam is coming. So okay, now maybe it's time, right? I will say more things, but before losing definition, sorry, let's give pictures. So one example is Contangent Bundles. So there and it's compact. Okay. So this is one example. One is like all of them are Liouville. Okay. So how? And for simplicity, I will just focus on, let's say, S1. Okay. So let's draw that picture. Okay. So this is stress one. So one thing is for dimensions, dimension 2 is very good to study symplectic manifold because first of all, you can take symplectic form as an area form. So you don't need to worry about that. Take what's my X and Y? X is this direction, Y is up direction, okay? So, okay. Take a symplectic form as this. Take your theta as locally 1 minus Y dx, okay? So that's your one form. And there's, I mean, you can compute that the corresponding vector field for this will be y times. Let's draw it. So what? Let's draw it different color. Let's draw it with blue. Which means it is actually zero in the zero, what you call? Zero section. It's zero. So then it grows. Or it grows downward. Etc. You understand the idea. So you're just escaping the zero section, okay? After zero section, it grows up and down. So this is Liouville vector field. Okay. So okay, maybe is it clear? So this is like a working definition, you know?
One thing to say to connect, like these kind of symplectic structures will arise in the complement of the divisor of a log Calabi-Yau variety.
Yeah.
That's an open thing, so it can admit this kind of structure. And sometimes the symplectic forms that you consider are of this nature, and then they're easier to work with, and you might want to understand their symplectic invariance, maybe using mirror symmetry, maybe without using mirror symmetry. Okay, so these are some nice examples of symplectic manifolds, and they will arise sometimes by equipping the interiors or complements of the divisors of log Calabi-Yau varieties with some natural symplectic structure.
But we use in this case only n-1. It's not the full filtration.
You mean this filtration?
So yeah,
So right now,
Question about like detail, let's maybe.
so I will say something about this. So I didn't use this filtration yet. So okay, so why this is a Liouville manifold, you say? Then you need to check, you need to choose growing cylinders, okay? Choose growing cylinders, M1, M2, M3, M4. And you will see this is always, this vector is always outwardly transverse the boundary, right? So therefore it's Liouville. So now I will talk about finite type Liouville. So right now this goes forever, okay? So it's not like I cut it somewhere, okay? This is like a infinite cylinder. So let me tell you then. Oh, but ask your question. Sorry, but
yeah,
that's
so my question was to be somehow like M1, M2, M3, or we listed only on.
so that's not a like a extra data. That's a condition. So if you can find such thing, that's you are fine. Okay, that's not like extra data. So but now you will see something. Okay, so I will talk about finite time. So first I will talk about skeleton. Let's keep that picture. So I will use that. I will give more examples also, by the way. So just let me first define skeleton. The skeleton, oops, this color is not good. The skeleton of a Liouville vector, Liouville manifold. First, which doesn't escape infinity under Liouville flow, okay? So that's that, but formally you can write like this. Now, so for each this compact set, you contract it using this flow. That's a union of them. So but instead of just think like a set of points on M, which that doesn't escape the flow.
So for the Contangent Bundles, it's
Yeah, so great. Under Liouville flow. Okay, indeed. So if you look at this example, take any point outside of the zero section, they will escape the infinity, right? Only the zero section will stay. So the immediate result that skeleton of Contangent bundle is it's zero section. And this example, just you don't need to work with S1. Okay. So we have this result. Okay. Are we fine with skeleton? Skeleton is important. Idea is this, so to study level, not just level, but Weinstein later, I will give one more condition to this. But idea is you study this manifold using the skeleton. So this is one good idea, okay, to attack this family. So understanding skeleton is important, but how skeleton recovers that? I will say some words on this. So maybe just one more definition before I pass to something. Finite type. Finite type level manifolds are where skeleton is compact. So when skeleton is compact, the thing is this, so you have this exhaustion, right? The thing is outside of the skeleton, this structure, symbolic structure is boring. It doesn't change, okay? I mean, it changed, but it just, you can recover all the symbolic structure. So, let me write this first. So, in that case, you can write M as M bar union its boundary times some ray, okay? There are this cooling happening along this. Where this M bar is one of this MI, so which contains skeleton. Again, near skeleton is something interesting happening, but after you take a compact pieces which contain skeleton, after that, it's just repetition. That means, you can restrict the one form here and do symplectization of this, and you can recover the symplectic form on this part. That tells you that this M bar is like compacting, right? Compact with boundary. So in this example, this goes like forever, like this. But M bar is this picture that you think here. M bar is this one. Think with boundary, okay? So basically, this is called cylindrical end. Basically, you can cut, if this is finite type, you can cut cylindrical end of a level manifold and work with this compact part, remaining compact part, which is called level domain, okay? So this level manifold. Okay, so I should speed up. I give examples, okay? Maybe. Speeding up is not super good idea if it's lecture. So, manifold. It's a pair of any surface actually, any puncture surface can be. What's the precise level of this sentence? I don't know, but any puncture surface can be seen as a level manifold. So, for example, pair of pens, upside down, Then, the two form is just the area form. Then I will give this vector field. So basically from now on, I'm just drawing the level domain, okay? So there's this, anyway, the colors, never mind. This is X. Level vector field escaping. And there's this region, which is skeleton. So let me draw this with different color. Yeah. You see? Or is clear the skeleton? It's like they said like a tongue, you know? Like a pants, this tongue, but upside down. And as you see, so here you see the singularity. That may be singularities, you know. Yeah.
It's okay.
It's okay. Sorry. Okay, so I will explain level sector and I will give Weinstein definition also. Level sector. So I won't be that precise. Level sector is like a Liouville manifold with boundary, kind of. Okay, so it's like a Liouville manifold with boundary. It's not like this boundary. This is the boundary of Liouville domain. Normally, Liouville manifold doesn't have boundary. Okay, we call this like infinite boundary, boundary at infinity, because actually it's not a boundary, right? I'm saying here the Liouville manifold has a boundary. Okay, but then you need to control behavior near this. So you ask such that, let's say you ask x to be such that x is tangent. Tangent. Okay. Sorry, this is not precise definition, but I did not define this, or I will give this to you. So, okay. Maybe let's give one example for this. I will give an example for this from this picture. Cut this two pieces like this. Take this blade, cut it like this. What you get? There's a front part and there's a back part, right? If I cut it like this. So you will get something like this. So see the vector field is along the boundary. I mean, here it doesn't need to be, but I mean, at infinity at least, it should be. So X is Liouville vector field, red is skeleton. Okay? I mean, you cut this like this, you get two of this piece, right? Or you can glue these two pieces to get this. And this is important.
So, like, you could also imagine cutting along the red, and it would also be tangent along the red. But is that doesn't count as a?
You mean like this?
Yeah, like you could take one of the legs and dance and cut it the red. And the vector field would still be tangent, right?
Cutting like this, you say, right?
Yeah.
It won't be tangent. I mean, definitely it won't. It's not a Liouville vector field, right? I mean, you're like cutting like that.
And you're saying, right? You left out part of the definition of vehicles.
Yeah. I mean, at the end, it shouldn't. It's not that something you want. I mean, basically, you should cut skeleton perpendicularly. I can also say like this: cut skeleton perpendicularly. Look at the skeleton. First, cut that, and first cut skeleton. Then just carry this rest of the piece accordingly. Make sense? Like I cut skeleton not along the singularity, maybe. Cut into the smooth part. Okay.
Can you just for me say again what is the M dash on the example is tangent to S1?
You mean M dash? You mean this dash?
Yeah, on that picture, it was
This picture.
Yeah.
This picture is M hat bar, M bar already. Because why? What you see is something compact, right? Imagine it goes forever. Then it says M. M is not. I cannot draw M here because it's a non-compact. It goes forever. So I didn't draw the cylindrical part. So actual M is like infinite height. Okay, it has infinite height. This one, which I cut some piece of it, is M bar actually. Okay, makes sense? You just cut the ends of it. So it's like cylindrical, infinite cylinder is M.
Yeah.
Actual cylinder, which has finite height, is M bar. So therefore, this is compact, that's not compact, right? Yeah. Wherever, right? Okay, so let me just give a definition of motion and go to flow theory, okay? Maybe I don't want to erase this part because for time reasons. Let's continue. So Weinstein manifold or sector, idea is this level vector field is usually is not that controlled, okay? So we want to give some control of it so that we have nice skeleton and some nice property between skeleton and the actual symplectic manifold. So that is yes. So it's level plus, actually I can start the exact symplectic manifold, but anyway, so level plus, there exists some function on L, exhausting Morse function. This means bound below and proper Morse. I mean, there are so many variations of this. Morse or Morse what you can take function. Such that this is like gradient like for x. So maybe let's say this is, I mean, sorry, x is gradient like, not gradient, but gradient like for it. That means this is equation holds for some delta. I mean, normally you can put one more term here, but I use this version of it. Okay. So this basically kind of control behavior of x. And as a result, the skeleton becomes an isotropic subset of what is isotropic?
Oh, sorry, all of it, so you're choosing some alpha complex structure.
Sorry?
You're choosing some alpha complex structure and you write all of it, so.
So here I don't need to choose an almost complex structure. This-
What is the norm with respect to norm?
Sorry? This norm, it's some Riemann metric. Choose a Riemann metric, any Riemann metric.
That's not some commutable metric.
I remember not. Okay. So that discussion is not here. Okay. So
Maybe just like a quick, like this is a general thing from dynamical system. This kind of, if you have this kind of function, then dynamics of such a vector field becomes simpler. For example, you can have periodic orbits. Because this function is always increasing along the flow of x. So you can't have a periodic orbit, for example.
So let me say something about now some particle subsets of N and then define replica category and then finish. How much time I left? Not much, but actually it's not 50, right? It's 1 hour talk. Okay, I have some time. So a subset is like isotropic if the symplectic form vanishes on it, okay? And it's furthermore, if dimension N, if plus L is dimension of N, L is N, where what is N dimensional? So assume this is 2N dimensional. This N dimensional isotropic subset means this is Lagrangian. Okay, so Lagrangians are submanifolds of your N, your Liouville manifold or exact symplectic manifold, doesn't matter. Which has dimension N and the symplectic form vanishes on them. But in exact setting, we care about exact Lagrangians. Okay, that's natural family. So we care exact Lagrangians, which are one form on L is not vanishing, but it's like exact. So this is exact. So which means for some function on your Lagrangian, if this equation holds, then it's exact Lagrangian. So this is isotropic, as you see. If it's in general a singular, right? As you see on this example, it doesn't need to be. Even if it's top dimensional, it doesn't make sense to say it's top dimensional. But if it's a top dimensional strata, we call it singular Lagrangian. Okay, so skeleton is usually singular Lagrangian or singular isotropic set. If it's not have top dimensional strata, actually its symplectic geometry is kind of boring, but in Fukaya categorical sense. Let's see. Maybe I should say those things later. One more thing, one more property for Lagrangians. Exact Lagrangian with cylindrical ends. As you remember, so we said this Liouville manifold has this boring part, cylinder part, right? We want our Lagrangians also just be boring there. Okay, yeah, if you like. So which means I just want to give you a Lagrangian in the Liouville domain, and you should be able to complete it to a Lagrangian. Okay, so this end means your Lagrangian can be written also this form. Okay, where L bar is in N bar. Make sense? This? So maybe in this picture I will give you some Lagrangians then. I mean, this is very classical Lagrangians, which is zero section is a Lagrangian. Okay. And cotangent fiber is a Lagrangian. Non-compact Lagrangian. So I give you two Lagrangians there. Okay. These are not just Lagrangian, these are exact Lagrangian. In two manifold, everything is Lagrangian already. This form vanish. Exact Lagrangian. I know. Yeah. Okay, now I'm ready to define replica category. But
give example of non-exact.
Non-exact Lagrangian. Okay, non-exact Lagrangian is something like this. This circle there. First of all, that area shouldn't be a positive area. Positive means what? So you count with sign. Let's say areas above zero section is positive area, areas below zero section is negative area. So that area shouldn't be non-zero. Maybe that's a good criterion for exactness. So certainly this is not the exact Lagrangian. Anything which doesn't intersect zero section is also not exact. It should intersect zero section. I mean, one can play with this equations and see this. It's not super hard to. You understand this? This is just I draw a circle.
The theorem is so clear. That's what we're doing.
Okay, so maybe now is a good place to stop. First of all, I mean, if you have question, so what we have so far, maybe let's recap. We have just this definition of Liouville manifold actually. So just this picture. Keep in mind this one. There was a picture here, which is double this pair of pens. Keep these models in mind. I mean, if you're confused, so those are Liouville manifolds we work with. Okay. This Weinstein condition, never mind. I mean, just it controls the behavior of this vector field so that you don't get a crazy skeleton. I mean, I won't write this down, but maybe I can tell you some stuff about this skeleton. In Weinstein case, the neighborhood of that skeleton actually determines, in any neighborhood of the skeleton determines all the Weinstein manifolds. So then, of course, one asks, can I study just skeleton and understand Weinstein manifold? They say topologically. That is wrong. Topologic type of skeleton doesn't recover Weinstein manifold. One example is puncture torus versus pair of pens. Maybe this is interesting. So let me just give you an example here quickly. The pair of pens puncture torus. Okay, so what are the skeleton? Assuming some little, I mean, I need to give you some. Vector field, but I mean, I can deform Liouville vector field in such a way that I can get this skeleton for the pair of pens. Okay, these two cuff. Let's see, 8, like 8. But this is, so just let me show you difference for pair skeleton. So pair of pen skeleton is like this. Okay. Puncture torus skeleton is like this. So, but inside two-dimensional thing, it makes sense, right? In topological sense, they are the same thing. So topologically, they are same, but obviously even their boundary components are different, right? This is 3 boundary components, this is 1 boundary component, so they are not equivalent.
Saying and it doesn't describe all the poles.
Sorry?
It means that P1.
What is P1?
It's a group of classes and groups.
Pi1 of skeleton or the thing. Yeah, that's not enough, definitely. Yeah. That's the question? Okay, so yeah, just I'm saying the topological type of this skeleton is so you definitely need the neighborhood of it. So in dimension 1, maybe this discussion I keep it here.
So people who are more familiar with algebraic geometry. So if you have a smooth, complex, affine variety, then that gives you an example of a Weinstein manifold up to some notion of equivalence. And for example, the fact that the topology of an affine variety like that, as like it goes only up to the half dimension, is kind of like a statement that the study of such a Weinstein manifold can be reduced to the study of this Lagrangian skeleton, which is half dimensional, into something that you could connect with.
Okay, so maybe one more. Actually, there was one nice property of this, which is there is a handle decomposition of Weinstein manifolds. So you can build them using handles. Okay. sorry, I'm just keep remembering some important stuff. One more thing is any Stein manifold is a Weinstein manifold, can be a Weinstein manifold or vice versa. What is Stein manifold? Maybe later, if you ask me, I can explain. But for now, I mean, smooth affine varieties are also Weinstein manifolds. That's important. Maybe that's relevant for this thing. So smooth affine varieties are Weinstein manifold. Or can be made with Weinstein manifold using their structure that I meant.
Silly question. This Lagrangian existence is not part of the definition of Einstein.
Even the existing,
Existence of this Lagrangian is not.
no, actually there is some manifolds which doesn't have a Lagrangians, compact embedded Lagrangians inside. Even.
Okay.
Yeah.
So why did you tell us this part? This part was not relevant for this.
It follows. If it's Weinstein, then it follows that the skeleton is isotropic.
But this can be singular.
No, that's just the definition.
Oh,
The definition of a class of Lagrangian.
Yeah, this is like this is a new part where I explain some important submanifolds of Weinstein manifold, which is very useful to study if you want to study Weinstein manifold. Okay, so I will denote it like this. I mean, Mark Gross said something about this, but actually not the rap version. So objects are those Lagrangians. Exact Lagrangians with cylindrical ends. Morphisms. So morphisms is not. So let me say like this. This is also not true. So you need to give an extra data plus extra data, like spin structure. But I will just work with the Z2 coefficient and Z2 grading so that you don't need to put this. Morphisms, so I will denote by home. So two Lagrangians, you give me two Lagrangians, L1 and L2. Morphisms are given by intersections of L1 and L2. So there are so many questions here, of course. This intersection should be, there should be finite many intersection, etc. So I will skip those discussions. But I will say something. So K is your coefficient ring. Okay. Which in this talk I will take it as Z2. But I will write K. So basically morphisms are generated by the intersections of L1 and L2. But this definition is not correct because L1 and L2 maybe intersect infinitely many points, right? So you kind of perturb L1. Maybe I should do it properly. So I use W for perturbation. So what kind of perturbation is this? It's Hamiltonian perturbation. And for non-compact ones, you do wrapping also on top of that. So maybe those concepts are best to explain on example. Because, again, time, I think. But maybe I will tell you what is Hamiltonian. Deformation is correct word? I forgot the. Yeah, so you choose a function on your manifold, and then you define a vector field corresponding to that using this equation, this XH. Hamiltonian vector field. And using this vector field, you move your Lagrangian. Okay? So that's how you perturb your Lagrangian. So if two Lagrangians intersect non-transversely, you just use this to make them transverse. There are so many details, so you should use time-dependent version, etc. But I skipped those things. And final part. So far, is it good? Actually, idea is this. We are studying intersections of, we are kind of, this is, I mean, square category is some machine or some collection of data of Lagrangians and their intersection. So it is something about this. So it's like huge thing. Well, one actual important part is infinity operations. So infinity operations are so it takes an input and gives you one output. Okay, so what inputs it takes? So you have Lagrangians L0 to Ln, okay? So you take one intersection of L0, L1, L1, L2, L3, L4, up to here. And you apply this infinite operation. So infinite operations are mu n for n is greater than or equal to 1. It's a collection of operations, okay? On the morphisms. So it takes an input and gives you one output. Okay, and how? What does it do? It counts holomorphic disks. Okay, so I will show it. The numbers. So let's say you have intersection P1, P2, and Pn. And then it gives you this sum. Q is just an element of this. So it runs along Q. And this number is given by this holomorphic test. So let me draw here. So assume you have this n plus 1 many Lagrangians, okay? And assume they bound a disk, okay? And let's say this intersection is a morphism, right? Intersection between Lagrangians is a morphism. So let's call this P1. This is P2 and P3, etc. This last intersection we call Q. So this is output. This last intersection is output. And then mu n of Pn P1 gives you equal to number of such disks, number of holomorphic disks of that form times Q plus the other things, of course, because maybe there's a Q, there's R, which also have this kind of things. Then number of this times Q plus that many disk plus R times R, etc. Is a bit strange. So of course I didn't. So okay, missing parts. What is holomorphic disk, right? There's no complex structure. So
Then many things missing. I think you don't try to fit these missing things.
yeah, so
The idea is that you have some Lagrangian, okay, they intersect at certain points, and you're trying to use these counts to define this kind of algebraic structure. Okay, so you input one intersection point from between Ln minus 1 and Ln, one between the other two, Ln minus 1 and Ln minus as in the picture there. And then you want to associate a formal sum of intersections of L0 and Ln. That's the kind of structure that we're trying to build. And the data that goes into this are that kind of polygon, but the polygon represents a special kind of disk mapping into a symplectic manifold. It's a holomorphic disk. Okay, so it's a special kind of disk. It's all the PDE. So there's rigid, for example, if you set up the problem correctly, you can find finitely many such things and actually count them.
yeah. And one more thing is sign count, etc. Also, our Lagrangians are graded, okay, which I didn't say. So this is like the points are also graded. So graded. Okay. So maybe I should say this, graded how? Grading of point is 0, let's say. So let's say Lagrangians are orientable, okay? So if I have this kind of intersection, it's like a root, not the right-hand rule, left-hand rule, that's 0. Of course, it all depends on convention, okay? So if you, maybe some of you won't agree. If you have this kind of intersection, it is odd degree, okay?
One question just to be sure. This sum in logarithms, is it taken over all possible wrapping or all possible wrapping?
Wrapping.
Yeah, you should at least know one thing.
Yeah, so wrapping, I didn't explain wrapping. So now it's coming. So this is the final picture. Maybe explain, answer your question for this set one, okay? Well, I have less than 5 minutes for this. Anyway, discussions time I can explain, but online participant, I don't know. So let me give you very quickly easier example first, so let's just choose the zero section, okay? And I want to compute this. Morphisms of L to L, okay? Of course, if you think about this, there are infinite many intersections, so you perturb it. So if you perturb it, it will be something like this. So I will call the perturbation WL, okay? So how many intersections you have? One. So let's give some orientation also, okay? Oriented like this, 1 and 2. So let's call it P and Q. So this is generated by 2 elements. Okay? Morphism between them. And then you look for holomorphic disk which bounds Lagrangian, okay? Actually, in dimension 2, there's Riemann mapping theorem, right? I mean, here, these are holomorphic disk, assuming. So, yeah, you're seeing this 2 disk, right? There's this disk, and there's this disk here, okay? And for example, you can say also the degree of this. So remember, you need to replace this with this. So first one is actually WL. If you look at like that, degree of Q is 0. This is 1, I think. Good. And there is mu1 operation from Remember, there was a mu1 operation. From this. This. Okay, there's mu2, mu3 also, but actually there's no, that, I mean, you need to check this actually, but let's just put the mu1 for now. And actually you can see, if you take Q here, Q goes to, there are two disks with the boundary Q and P, and L0 and L1. With that, this picture is very rigid actually, the order is also important, okay? With that order, P doesn't go to Q, but Q goes to P, okay? If you really fit this picture. And if you see the two disks of this form, therefore Q goes to how many holomorphic disks? We have that form? 2 times P. So we have this holomorphic disk. There are too many of this holomorphic disk. Therefore, Q goes to 2 times P. But we are working with characteristic 2. Therefore, this is 0. Okay? So this is mu1 structure. I mean, if you didn't work with Z2 grading, actually, we do count holomorphic disk with sign. So actually, it will be +1, -1. It will be again 0. Okay? Okay, I don't have much 0 time left, so let's just wrapping and wrap things up. Okay. Okay, final picture, which I don't count any holomorphic on it, but you can ask me later, okay? I can share my notes, okay? There you can see. What if I take this Lagrangian and look at this thing? Okay, what are the intersections? So this time, you again perturb with Hamiltonian, but your Hamiltonian should, along the boundary, its flow should be along the rip flow. Okay, so remember I give you some rip flow, right? So there is a rip flow actually in this direction here, and the rip flow in that direction here. So your Hamiltonian flow should, when you restrict here, should be along this direction. And there's some statement about the speed, but I will take, so normally you can do step by step and then take limit, which means.
Let's draw a picture for once because there's no time.
Okay.
And then we can just like the limit case, the quadratic.
Exactly. So just the limit case. So then you wrap forever. So which means you don't wrap finitely many. And you just wrap this forever. Okay, so then you get this. I mean, it wraps forever here, forever there. Okay.
Creates infinitely many intersection points.
So it creates infinitely many intersection points here. So this is actually given by the intersection point can be labeled by integers, if you like. So actually it's like k times z, if you like. Yeah, it doesn't matter right now because there's no structure, but then there's a structure also coming from holomorphic disk. And that is actually all the mu ends vanish except mu2. And mu2 is just doing this. And all the other mu vanish. I mean, that's exercise, but we can work together, how I see this. Okay?
So maybe better to write polynomial, not crazy, right? But K.
Yeah, so then I mean, then you want to like this, right? Like this, which reflects this product structure. Okay? Because of this condition.
Let's,
Okay, sorry.
okay, maybe one question.
It's going to be right like this. I mean, this example I take, but I mean,
Sorry?
I mean, okay, this example I get it right, like this, but I mean, it's just the only example you can do, right? Right? What, like what? Like right in practice, the opening is ring there.
You mean this one?
Yeah.
Okay, that's coming. So I didn't say some stuff. So there's infinite operations, right? Mu1, mu2, mu3. I said that. Mu1 is like a differential, if you think. Okay, and mu2 is like a product. So I am saying this intersection has this property. So actually, instead of writing x to the x sub I, it's like x to the power I, if you think about that. Right? Because x to the power I times x to the power j is x to I plus j. So I mean, these intersections are generated by x and x inverse. I mean, for example, I'm just saying this intersection, I call it 1, this x square, right? Mu2 of this x twice gives you x square. So this mu operations on your replica category, and this two intersections generate all the other intersections. But via this mu2. I mean, I can apply mu2 to this x.
I mean, you have to compute these products. You have to,
Not just in this.
no, it's not always such a nice limit. It's
Oh, yeah.
only very rare that it's something like this. It's not even an algebra generally. It's an infinity algebra. But in this case, it happened to be very nice. It's an important computation. But even this is not trivial, and you will need to do something to really be able to say this precisely.
I mean, normally mu2, mu3, and mu4 even they don't vanish. So it doesn't. I mean, this is just this kind of things you can say when mu3 and mu4 vanish, and then you can say, okay, this is differential and product structure. That's it, and then you can describe like this. But normally, yeah, normally it's that kind of very complicated thing. Okay, yeah.
Okay, so the question, let's continue after thanking our speaker again.
One last comment is you can glue this stuff also, which I plan to do, but
So
that's for later then.
for ending our session, I don't know if they can actually hear me. I forgot this.
You mean from here?
Online participants, can you hear us?
They gave up already.
No, I can hear you.
Yes, okay. Well, this is the end of the session for today, and maybe see you tomorrow. We hope to see you. Okay, bye.
It's worth giving a better answer to your question. The guy in so it's true what those guys are saying, but the subject of marriage agree with himself. That's what is it brings a miraculous version.
So we want to actually explain everyone. So we are going to have a discussion session. So we have to decide whether we take a break or continue or
I probably we're probably going on. But
okay.
I say the same. There's